Now let's start with question number 1 of the EOT. Explain how the relative motion between a conductor such as a wire and magnetic field causes an induced EMF. So before we move to the question, first of all, the relative motion between a conductor such as a wire and a magnetic field causes an induced EMF. So think of this like imagine this is a wire, okay? And this has been placed in a magnetic field which is cross. When we say cross, that means it's going into the board. When we say dot, it is coming out of the board. Now this wire, I'm moving in a certain direction. Let's say this particular wire is moving. Now, if this is moving in this direction, what is happening? On a metallic wire or on a conductor, there are charges like electrons exist on the surface. Now, when there are charges, that means I'm moving the charge basically in the magnetic field. And because I'm moving the charge will experience a force which is given by QVB sine theta. This we discussed in term 2. Now, if that is the case, then we need to find the force on the charge. So the force on the charge will be, take your right hand, place the fingers of your right hand towards the magnetic field. So this is the direction of towards the velocity. So this is the direction of the velocity, the speed. I can place it in any direction, provided my fingers are pointing in the direction of velocity. Now, if velocity is here, I have to curl my fingers towards the magnetic field. Now, magnetic field is into the board. So I cannot curl it like this. I will have to turn my fingers towards this, pointing in the direction of velocity, and curl it towards the magnetic field, which is into the board. Thumb is pointing up. If thumb is pointing up, that means all the positive charges will get collected at the end, at the left end. And all the negative charges will get collected at the right end. So if they ask you the question that which point of this has a higher potential, so all with the positive charges will have a high voltage or high potential, and this one is the low potential. Basically, this, while it is moving, will behave like a battery, which is positive here, negative here. And now, if I connect it with any wire, any resistance, any electric lamp, what would happen? This would produce a current, and the current will be from positive to negative. So the current will be in this direction like this. If they ask you what is the current in the wire itself, which is moving, it is in this way. Remember, if the wire alone is moving, there is no current because it's an open circuit. It is not a completed circuit. But sometimes they ask you questions like that. So you can say that the current is going to be from negative to positive in the wire itself. But if I join it with a proper complete circuit, in that case, this will be the direction of current, which is going from the positive terminal to the negative terminal. This basically behaves like a battery. This rod behaves like a battery. This is what the induced EMF is, or V induced. Actually, it is EMF. V induced, and this is given by VL, V sine theta. V is the magnetic field, L is the length of the wire, V is the velocity, and theta is the angle between the velocity and the magnetic field, or basically the length here. When the wires start to move, the charges inside, okay, we have discussed this already. See, there will be tons of different rules which are there in your book and everything. You can use whichever rule you find comfortable, like you are comfortable with. In this case, the thumb is pointing with the velocity, fingers are the magnetic field, and this will represent the force. In the case which I told you, fingers are pointing in the direction of velocity, you're curling your fingers towards the magnetic field, the thumb will point the direction of force. Again, slow it down and try to use whichever rule you are familiar, like you can familiarize yourself with, or whichever you see, it seems easy to you. So theta is the angle between the field and the velocity. The voltage is VLV sine theta, and you already know as per Ohm's law, it is V is equals to IR. So current will be voltage over R. Now whatever this voltage is divided with the resistance, you will get the current. Let me remove this if I can. Okay. You move a straight wire that is 0.5 meter long at a speed of 20 meter per second vertically through a 0.4 Tesla magnetic field pointed in the horizontal direction. What EMF is induced? Majority of the time, the angle will be either 90 or 0. Remember, the angle is between the velocity and the magnetic field. So if the rod is moving parallel to the magnetic field, the EMF will be 0 because sine 0 or sine 180, basically if they are parallel or if they are opposite. Therefore, EMF will be 0. But if it is theta is equals to 90, that means the velocity and the magnetic field are making an angle 90 degree with each other, then EMF will be maximum because sine 90 is 1. Majority of the cases you will have theta is equals to 90 degrees. So in this case, for example, at a speed of 20 meter per second vertically, magnetic field pointing in the direction horizontal. So vertical and horizontal, the angle between them is 90 degrees. All you have to do is put the formula, you'll get the result. The wire is part of a circuit with a total resistance of 6 ohm. What is the current? Again, use simple Ohm's law. You will get the value of current. I is equals to voltage over resistance. A straight wire that is 25 meter long is mounted on an airplane flying at 125 meter per second. Okay. The wire moves in a perpendicular direction through Earth's magnetic field. Where is the wire? It's mounted on an airplane. Okay, we don't know the location of the wire. The wire moves in a perpendicular direction through Earth's magnetic field. What EMF is induced in the wire? Okay, we don't need to know because here it is said saying perpendicular. So theta is 90. All I have to do is put the formula BLV sine theta and I will get the value of the EMF induced in the wire. A straight wire segment in a circuit is 30 meter long and moves at 2 meter per second perpendicular to the magnetic field. Similar question. A 6 volt EMF is induced. Now this time they have given you the EMF. What is the magnetic field? So I know the current, I know the length, I know the velocity. A straight wire 6 volt, I know the EMF. So EMF is BLV sine theta. Theta is 90. EMF is 6 equal magnetic field. I don't know. Length is 30. Velocity is 2. Theta is 90. So sine 90 is 1. I'm left with this. Solve for X. You will get the magnetic field. The total resistance of the circuit is 5 ohm. What is the current? Again, if you have the EMF, you just have to divide it with the resistance. You will get the current. A 10 volt EMF is induced in a circuit and the total resistance of this circuit is 5 ohm. What is the induced current? Simple question. A conductor moves with 8.5 meter per second speed perpendicular to 0.3 Tesla magnetic field. A 0.68 volt EMF is induced. What is the length of the wire? Again, similar equation. All you have to do is the different values will be asked at different times. Sometimes they will give you the EMF. Sometimes they'll give you the magnetic field. Sometimes they will ask for the length. Sometimes they'll ask for the velocity. Sometimes they might again ask for the angle, theta. So remember, all you have to do is put sine theta is equals to X, solve for X. Now, whatever is the X, theta is equals to sine inverse of that value. The sine inverse is also in your calculator. You can find out the angle. Or I hope you can actually put this as X and solve for X. Your calculators are capable enough to find the value of the angle as well. At what speed would a 0.5 meter length of wire have to move across a 2 Tesla magnetic field to induce EMF? Similar question, same expression. Here you have to find out the velocity. Which of the following is a real life application of induced EMF? Induced EMF means because of the magnetic field and the movement of the conductor, there must be a current induced. So in digital camera, none. Electric heater, none. Light bulbs, none. Microphone, yes. In microphone, we do use electromagnetic induction. What happens is basically when I'm talking, so in the microphone, what is happening because of my sound waves, the coil inside the microphone that vibrates, and because of that vibration, an electric current is generated, which is transmitted to the device to basically like record it or whatever it is. We have discussed the functioning of the microphone in the class. What does the induced EMF depend on? Choose all the correct ones. All the things like magnetic field, length, velocity, angle. So if a wire moves perpendicular to a magnetic field, the strength of the magnetic field, the length of the wire, the speed, the angle between the velocity, the shape of the wire, actually it does, but eventually it will come to as closed loop systems where the area matters and the flux. We are not going in that detail. The type of the measuring device, none. In which case of the following does the EMF have the greatest possible value when theta is 90 degrees? Because sine theta has the maximum value as 1, so it needs to be perpendicular. Figure show the circular coil immersed in a regular magnetic field perpendicular to the coil's surface. Okay. The coil is rotated in a magnetic field as shown in the figure. So we have this coil and it is being rotated. What happens when the coil is rotated in the magnetic field from the position figure A to figure B? So we have discussed this in class. There is something called magnetic flux. Flux means the number of field lines which are penetrating. That means which are going through. So here you can see that most number of field lines are going through this particular area or this particular loop. When I'm turning it, now what is happening? The most number of field lines are parallel to it, but nothing is penetrating. So there is a flux change. Flux is represented by phi, magnetic flux. So the magnetic flux is reducing. And because the magnetic flux is changing, as per the Faraday's law, there will be an EMF generated. That means there will be a voltage generated. So an induced electromagnetic force is generated. Induced current is generated because the coil is closed. That is why the induced current is generated. When the coil is rotated in the magnetic field, the change occurs in the number of magnetic field lines that cross the coil. Same thing, which I explained to you. You can read it and basically go through it. It will give you the answer. Figure 1 shows two magnets, the north pole. Oh, this was the question asked last year. Figure shows two magnets, the north pole N of the first magnet faces the south pole S of the second, okay, as shown in the picture. The length of each is 20 centimeter and the height of each is 6 centimeter. So they have given you this length, they have given you the height as well. Between them is a uniform magnetic field of strength. The magnetic field is given. A taut wire connected to a milliammeter was moved from the lower end of the magnet to the upper end perpendicular to the direction of the magnetic field lines during a time period of 0.2 second as shown in the figure. Calculate the following. See, nowadays what they have started doing is specifically in advance, they ask applicative questions. That means you have to understand what is happening in the situation. Using the formula directly might not work. So that is why I would recommend you to go through the question in Arabic and in English to understand what is happening. Here, we are moving a wire up and down between the two magnets, but they have not given us the speed, but they have given us that this is the height and the wire is going from down to up in a certain time. So I know the distance, I know the time, can't I find the speed? What will be the speed? Distance over time. What is the distance? The height is 6 centimeter. That's the height. So 6 centimeter, that means 0.06. I have to change it to meter. Over time it takes is 0.2 seconds. So 0.2 seconds. This is the velocity of the wire. They have not given the length of the wire. But what is the length of the wire which is exposed to the magnetic field? Only this part is exposed. So this is the length of the wire, same as the length of the magnet. So what is the length of the wire? 20 centimeter. 0.2 meters. I have the length, I have the velocity, I also have the magnetic field, which is 54 millitesla times 10 power minus 3. What do I have to find out? The induced electromotive force. That means V induced. V induced is BLV sine theta, and the angle between the magnetic field and the wire is 90 degree and the velocity is 90 degree. So just put the value, you will get the result. The induced electric current passing in milliammeter, if you know that the electric resistance of the circuit is 2 ohm, can we find out the current? Yes. If I have the voltage, sorry, EMF, I will come out to be V over R. I have the resistance, I have calculated the EMF, just divide it, you will get the result. This was a writing question last year. Explain how the relative motion between a conductor such as a wire and a magnetic field. Same thing, apply the right hand rule to determine the direction. Again, similar questions, similar sets of questions. A conductive wire, just the explanation. A conductive wire moves to the right through a magnetic field as shown in the side figure. As a result, a magnetic force is generated that affects the charges in the wire, working to redistribute and separate the electric charges, correct? The separation of charges produces an electric field and hence a potential difference. Okay. Along the wire, what is the direction of the induced current flowing through the conducting wire? First of all, the induced current will only flow if this particular wire is connected, like the circuit is complete. So that is very, very important. So we are assuming that the circuit is complete. What is the direction of the induced current flowing through the wire? First of all, motion is here. This is north, this is south. So the magnetic field is in this direction. So as I told you, what exactly do you have to do? Place your fingers towards the velocity. So let's say this is north, this is south. This is a three-dimensional figure. This is north, this is south. So the magnetic field is coming from here to here. in this direction. Velocity is in this direction. It is going here. So the rod is going here. The velocity, I'm keeping my fingers in this direction. Towards the magnetic field is here in this direction. So can I curl my fingers? No, I will have to turn. Velocity is still here. Curling my fingers, thumb is pointing up. That means in this wire, all the positive charges will get collected here. And all the negative charges will get collected here. So what will be the direction of current? So all the positive charges will start moving up. So this will be the direction of current from down to up. So this is the answer. Just go through it, check out the direction. You can use again any rule, it does not matter. At the South Pole, the Earth's magnetic field is directed upwards. If a plane is flying over the South Pole, as in figure, which is taken from above, which wing will have the higher electric potential energy? Okay, first of all, here they should not have asked electric potential energy. Rather, the question should be electric potential. Why am I saying not electric potential energy? Because to find the absolute electric potential energy is impossible. You always have to take a reference. In general, the reference is taken at infinity. So we are assuming that here they are taking the reference as infinity. But the correct question or the better question would have been to ask electric potential. Although the answer wouldn't differ here, but still. Now, this is a plane. They're asking what is the electric potential across the wings or electric potential energy across the wings. The magnetic field is dot. Velocity is here. So I'll place my fingers towards velocity, curl it towards the magnetic field. Now magnetic field is coming out if you consider this situation. So if I place my fingers like this, I cannot curl it this way. So I'll have to go this way. Curling my fingers is here. All the positive charges will go down. So this is the positive charge and all the negative charges will come up. So this is at the higher potential. This is the lower potential. The right wing is at the higher potential. Which of the following is correct when conductor AB moves with the speed V as shown? So if we have to find out, the cross magnetic field is there, that is going in, the velocity is down. So velocity is down, cross magnetic field is in, thumb is pointing up. So this is the positive charge collection. This is the negative charge collection. The conductor works as a battery, correct. Where is a positive, where A is positive and B is negative. No, wrong. B is positive, A is negative. The conductor works as a battery where A is negative and B is positive. This is fine. No current is induced. The current will be into the page. No, these two are wrong. The option is B. What is the direction of electric field in the wire below if it was pulled to the left? What is the direction of electric field in the wire below if it was pulled to the left? If we are pulling it to the left, velocity is here, magnetic field is out. So I'll place my fingers towards velocity, magnetic field is out, thumb is pointing up. So this is positive. This is negative. The direction of electric field, positive to negative. Electric field will be, what is the direction of electric field in the wire below if it was pulled to the left? This is the positive, this is negative. Electric field in the wire below. Electric fields are generally from positive to negative, so it will be from the direction like basically going down. But in the beginning, when the separation will happen, at that point what will happen? The positive charges will start moving towards away. So in the beginning, it would be in the upward direction. Okay, this is an interesting question. What is the direction of electric field in the wire below if it was pulled to the left? Okay, I'll explain it. If electric field is this, in that case, if I place a positive charge, now this positive charge moves in the direction of electric field because electric field lines start from positive, enter into negative, as in like discrete. So the positive charge pushes and it goes towards the negative side. Now here, what is happening? Right now, all the charges on this particular rod are randomized. They are moving in random directions. Once I start moving it here, then what happened is the velocity is here, magnetic field is out, thumb is pointing up. So there is an electric field generated in this particular wire because all the positive charges are being pushed up. So as per me, when we just start moving it, the electric field is upward. Once it has gone on settled there and I'm still moving it, then I can say that the electric field generated because of this will be downward. So as per me, the answer should be upward here. maybe they are considering a situation which is after the settlement of the charges or the electric field generated because of the charges in the wire. Anyway, the direction of the induced current in a wire moving through a magnetic field can be determined using the right hand rule. Which number on the finger indicates the direction of the wire's movement through the field? So this is the rule which is given in your book. So in this case, this one represents the velocity, this represents the magnetic field. They are asking the wire's movement, so that is the velocity, and this will represent the force. So I think V, magnetic field, and force. A conductor moves with a 4 meter per second speed in a 0.2 Tesla magnetic field. What is the induced EMF and what is the direction of the induced current? Magnetic field is dot, rod is moving in this direction, so velocity, magnetic field is dot, so I'll have to curl my fingers towards this, thumb is pointing down. So this is positive, this is negative. What is the direction of induced current? This behaves like a battery. So the direction of induced current is this. Sorry. C to D. So 0.04 volt from C to D. You can calculate 0.04 volt using the equation DLV. Relate effective current and effective potential to the maximum values of current and potential in an AC circuit. So we have discussed AC in detail in the class, but I'll just quickly go through it. When we say alternating current, what we mean by it is that in the wire, the electrons or the charges are moving randomly right now. When we say DC, what happens? One electron, or basically the charge behind, starts pushing the next charge and they drift away in unidirection. In AC, what happens? Remember, current is not charge, current is the rate of flow of charge. So there are charges. In AC, what happens? The charge starts moving and pushing the next charge. It speeds up and then starts pushing the charge. The moment it rises to a maximum value, like the speed becomes maximum, it needs to stop. So because the polarity of the battery changes. And when the polarity changes, then it slows down, stops, starts coming back, then again goes in the opposite direction, slows down, stops, then starts coming back. And the charge keeps oscillating left and right at the same point. While it is oscillating, its velocity or the rate at which it is flowing, it increases, reaches a maximum, decreases, stops, becomes negative, that means in the opposite direction, and then comes back here. This is the alternating current, IT, with respect to time. So the current is maximum here, which we generally represent with Imax or sometimes also I naught. But when we talk about the current which is being measured, because the current is continuously changing, the usual frequency for change is 50 to 60 hertz. In the States, in US, it is 60 hertz. In here, like UAE and different parts of the world, sometimes it's 50 hertz as well. That depends that how fast or how rapidly your devices which you are using can handle the change. Anyway, this is Imax. But the meters which we use, they calculate the energy which is being dissipated in a certain amount of time, in a fixed interval of time. And that meter measures I effective. And I effective, or it is also called as IRMS, is given by I maximum over √2. Now, this can be for current. It can be also for the voltage, V effective, same way, V max by √2. But for resistance, no. Resistance is the property of the material. It is a character, basically, there. So V max by √2, R will be R. So in simple terms, if they are asking to find I effective, you will use V effective over R. If they want you to find I max, you will use V max over R. If they're asking you max, use max. If they're asking you effective, use effective. If they want to find power average, power is VI, remember. When we solve it, the average power comes out to be V effective times I effective. If they ask you power maximum, it will be V max times I max. So accordingly, you can solve. These are the values which they have given. Here they have used √2 by 2. It's completely up to you. It is I max by √2. If I multiply and divide it with √2, this becomes √2 I max. and this becomes root 2 times 2 is 2. So you can use this expression also. This comes out to be 0.707. It's completely fine, completely up to you which result you wanna use to. Again, same thing. I have told you this, P effective and like the power. And also you can think of like power average, as I told you, is V effective, I effective. Power maximum is V max, I max. So V effective is V max by root 2. I effective is I max by root 2. So V max by I max is what? Power max, and root 2 times root 2 is 2. So I can say that power average is power max over 2. Graphically, you can see that as well, that this is the maximum power and this is the average power in between. And power will always be positive, remember, it won't be negative. So that is why you can say that the curve is above. A generator develops a maximum potential difference of 170. What is the effective potential difference? You can calculate it. All you have to do is, I have V max, I have to find V effective, divided with root 2, you'll get the result. A 60 watt lamp is placed across the generator with an Imax of 0.7. What is the effective current? You have Imax, you have to find effective, just divided with root 2, you will get the result. What is the resistance of the lamp when it is working? Remember, when you are using V effective, then you use I effective to find out the resistance. When you are using V max, use I max to find out the resistance. So here you have the I effective, you have the V effective. All you have to do is resistance. That will be V is equals to IR, and resistance will come out to be V over I. So V effective over I effective. You can do 120 divide 0.5, that will come out to be 240 ohms. Or you can use power expression for power, that's completely up to you. The RMS potential difference. RMS is root mean square. It is effective. Potential difference of an AC household is 117. What is the maximum? So V effective is given is V max by root 2. All you have to do is just divide the value. If RMS current through the lamp is this, what is the lamp's maximum current? If you have the RMS current or effective current, just multiply it with root 2, you'll get the maximum current.